So in the first video on radicals and rational exponents, we looked at square roots and we looked at cube roots. And every time we were doing a square root, we had a perfect square under the radicand. When we were doing cube roots, we always had a perfect cube under the radicand. It made it easy, but what happens when maybe you don't have a perfect square under the radical? So let's say we want to take the square root of 162 here. 162. So if we look through our perfect squares, notice that 162 doesn't show up in the list, right? 162 would be somewhere like in between 144 and 169. So it's not a perfect square. So the question is, what do we do? What do we do when what's under the radical is not a perfect square? Well, what you want to do, you want to factor your number 162, if possible, into two numbers where one of those numbers is the largest perfect square you can come up with. That's a factor of 162. So I'm going to write this as the square root of. So think about 162. You can break that down into 81 times 2, right? 81 times 2. So the 81 is a perfect square, right? 81 is a perfect square. Where is it? It's right here, right? Right there. 81 is the same thing as 9 squared. So now what I'm going to do, I'm going to take the square root of 81. The square root of 81 is 9. Why? Because 9 squared would give you 81. So I'm going to pull a 9 out. When I take the square root of 81, I pull a 9 out front. I leave the radical, square root symbol, and 2 doesn't get out of jail because he's not a perfect square. 2 has to stay in jail because he is not a perfect square. So 9 times the square root of 2 is going to be our reduced answer. Or we could say 9 square roots of 2. All right, let's do another. Let's say I have square root of 432. So this one might be a little tricky. So what do you do? So 432 is not going to be a perfect square. Turns out it's not. If I were to do 21 squared, for example, 21 squared, I'm not even sure what 21 squared is. That's 441. So 432 is somewhere in between 400 and 441. It's not a perfect square. So what we're going to do, we're going to figure out, okay, what can I break 432 down into? What can I factor it down into where one of the numbers is a perfect square? So sometimes it's not always to just think in your head. So the first one was pretty easy. 81 times 2, 81 is a perfect square. This one's not so easy. So I'm going to make a factor tree. Come up with all the prime factors of 432. I'm going to start off with 432. And we know that's divisible by 2 because it's an even number. So I'm going to have 2 times what gives me 432? I'll take 432, divide it by 2, and we get 216. Now 2 is a prime. 216 is not a prime, right? 216 is divisible by 2 because it's even. 2 times what? 108 gives you 216. So I'm going to circle my primes. 108 is not a prime. It's even. It's divisible by 2. 2 times what? 54. We can circle 2 because it's prime. 54 is not prime. It's even. We can divide it by 2. 2 times 27 gives you 54. 2 is prime. 27 is not prime. 27 breaks down into what? 3 times 9. 3 is a prime. 9 is not a prime. 9 breaks down into 3 times 3. These are all primes now. All right, so we have a bunch of copies of what? 2. We have 1, 2, 3, 4 copies of 2. We have 2 to the 4th power, and we have 3 to the 3rd power. So that's the prime power factorization of 432. 2 to the 4th power times 3 to the 3rd power. All right. So what we're going to do, we're going to work through this problem. That was just some warm-up showing the prime factorization. Let me go green here. So what I'm going to do, I am going to leave prime powers around that are even. So I'm going to leave 2 to the 4th power there. Anytime you have an even power, you're going to have a perfect square. So we have 2 to the 4th power, you're going to have a perfect square. Now 3 to the 3rd power, notice this is not an even power here. This 3rd power is not an even power. So what we're going to do, we're going to break this up into multiply by 3 to the 2nd power times 3. So I'm basically separating 3 to the 3rd power as 3 to the 2nd power times 3. So this even stuff right here, this even powered stuff right here, that's going to give you a perfect square. Anytime you have an even power, you're going to have a perfect square. Odd powers will not have a perfect square. So basically what we did, we peeled 1 3 off of that 3 to the 3rd, and it gave us 3 squared. Now let's take 2 to the 4th. 2 to the 4th is what? 16. Let's take 3 squared, that's 9. And then we have times 3. Now, in jail right now we have 16, we have 9, and we have 3. So what we're going to do, we're going to get 16 out of jail. 16 is a perfect square, right? 16 is a perfect square, so it can come out of jail. When it comes out of jail, it becomes 4, right? The square root of 16 is 4. 9 is also a perfect square. So he gets out of jail as well. He becomes 3, right? The square root of 9 is 3. Now, who has to stay in jail? Well, that red 3 has to stay in jail. He doesn't get out of jail because he's not a perfect square. So to simplify this, we're going to do that 4 times 3 in front of the radical. 4 times 3 is 12. So 12 square root of 3 is going to be your final answer. So there are a number of ways to do this, but this is one nice way. All right, so let's do another. How about the square root of 3 times the square root of 15? Square root of 3 times the square root of 15. So the way you actually multiply two radicals, you make a common radical, which in this case, if they are both square roots, you make a common square root, and then you multiply what's underneath together. You take 3 times 15. Well, that's going to give me the square root of, well, 3 times 15 is 45. Is 45 a perfect square? What were our perfect squares? No, 45 is not a perfect square. So what we can do, we can break up 45 into two numbers, where one is a perfect square and the other is not. We're going to break it up into 9 times 5. So we're going to have 9 times 5. Right, 9 times 5 is 45, and 9 is a perfect square. Square root of 9 is 3. So 9 gets out of jail, becomes 3. And under the radical, I leave a 5. So that's my answer, 3 square roots of 5.